I want to talk to you about the way the world really is. Not the way it looks to your eyes, or the way it feels when you touch a table, or even the way it makes sense to your common sense. I want to tell you about the way nature behaves when she is left alone, down deep at the very bottom of things. And I have to warn you right now, you are not going to understand it. You might think I am saying that because the math is too hard, or because you need a fancy degree to get it. No, that is not it at all. I am saying you won't understand it because I don't understand it. Nobody does. The way nature works at the level of atoms and electrons is just strange. It is absurd. It goes against everything you know about how things should move and act. If I tell you that a baseball can be in two places at once, you would tell me I am crazy. But if I tell you an electron can be in two places at once, I am just telling you the truth. The problem we have, the reason this is so hard, is that we are giants. We are these huge, clumsy things made of billions and billions of atoms, and we live in a world of big things. We are used to heavy stones and splashing water and things that stay where you put them. We have developed a common sense that works perfectly for avoiding tigers or catching a ball, but it is absolutely useless when we try to look at the tiny particles that make up that ball. So, for this time we have together, I want you to relax. Do not try to force these ideas to make sense in terms of what you see in your kitchen. Just accept that nature is a little bit crazy. If we can admit that, we can actually learn something beautiful. We can learn the rules of the game, even if the game seems like it was made up by a trickster. We need to start with an experiment. This is the one experiment that has all the mystery of quantum mechanics inside of it. If you can really wrap your head around this one situation, you have faced the central problem of modern physics. We call this the experiment with the two holes, or the two slits. To understand why it is so shocking, we have to do it 3 times. First, with something you understand, then with something else you understand, and finally with something that will blow your mind. Imagine we have a machine gun. It is not a very safe experiment, but this is just in our heads, so it is fine. We have a gun that shoots bullets. In front of this gun, we place a steel plate that has 2 holes in it, slits tall enough for a bullet to pass through. We will call them hole number 1 and hole number 2. Behind that plate, there is a backstop, a thick wall of wood or sand. Every time a bullet hits the backstop, it gets stuck there, and we can go count them later. So we start shooting. We are not very good shots, so we spray bullets everywhere. Some hit the steel plate and bounce off. We don't care about those. But some bullets go through hole 1, and some go through hole 2. After we shoot a few thousand rounds, we walk around to the backstop to see what happened. What do we see? Well, it is obvious. Behind hole 1, there is a pile of bullets in the sand. Behind hole 2, there is another pile of bullets. If we drew a graph of where the bullets landed, we would see 2 bumps. One bump matches up with hole 1, and the other bump matches up with hole 2. The bullets travel in straight lines. They go through a hole, and they hit the wall directly behind it. This is how particles behave. They are little lumps of stuff. They go here, or they go there. No magic. This is the world you know. Now, let's change the game. We are going to get rid of the gun and the bullets. Instead, we are going to do this experiment in a swimming pool. We put up a barrier in the water with 2 small gaps in it, hole 1 and hole 2 again. On one side of the barrier we have a machine that bobs up and down, making ripples, making waves. The waves spread out from our machine. When the water wave hits the barrier, most of it is blocked, but small waves start to spread out from hole 1, and small waves spread out from hole 2. It looks like 2 stones were thrown into the water at those spots. These 2 new sets of waves spread out and head toward the back wall of the pool. Now, this is where it gets interesting. Water waves are not like bullets. They are not hard little lumps. They are a movement of the water. What happens when the waves from hole 1 meet the waves from hole 2? They interfere. You have probably seen this in a bathtub or a lake. In some places a crest, a high point, from wave 1 meets a crest from wave 2. They add together to make a super high wave. We call that constructive interference. But in other places, a crest from wave 1 meets a trough, a low point, from wave 2. The high water fills in the low water, and they cancel each other out, the water goes flat. We call that destructive interference. If we look at the back wall of the pool, we don't see two simple piles like we did with the bullets. We see a pattern. We see a spot with lots of splashing, big waves, then a spot with calm water, no waves, then another spot of big splashing, then calm, and so on. We call this an interference pattern. It is the fingerprint of a wave. If you see this pattern of stripes, strong, weak, you know you are dealing with waves. This is also part of the world you know. Sound does this, light does this, water does this. So far everything is fine. We have lumps, bullets, that make two piles. We have waves, water that make an interference pattern. Now, we are ready for the third experiment. This is where we leave the world of common sense behind. We are going to use electrons. Electrons are tiny particles. We know they are particles because we can count them. When you have a Geiger counter, it goes click, click, click. It doesn't make a whooshing sound like a wave. It counts 1, 2, 3. They arrive as little lumps. So we set up our electron gun, basically the thing in the back of an old TV set. We put up a plate with two tiny slits, and we put up a screen at the back that glows whenever an electron hits it. Click, a flash of light. We start firing the electrons. To be very careful, let's fire them one at a time. Click, an electron leaves the gun, goes through the apparatus, and hits the back screen. Click, another one. We are seeing individual flashes on the back screen. Each electron lands at one specific spot, just like a bullet. It seems like we are back to the first experiment. These are particles. They are tiny bullets. So we sit there for an hour letting the electrons click, 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 one by one. We wait until thousands of them have hit the screen. Then, we look at the pattern they made. If electrons were just tiny bullets, we should see one pile behind hole 1, and one pile behind hole 2. We should see two bright spots on the screen. But we don't. When we look at the screen, we see the interference pattern. We see stripes. We see a bright band in the middle, then a dark space, then another bright band, then a dark space. It is exactly the same pattern we saw with the water waves. Stop and think about how impossible this is. This is the moment you should be confused. If you are not confused, you haven't really heard what I said. We fired the electrons one at a time. One single electron left the gun. It traveled through the vacuum. It arrived at the screen and made one single flash. It didn't break apart. It didn't spread out like water. It hit one spot. Yet, after we fired thousands of them, their landing spots arranged themselves into the pattern of a wave. How does a single electron know where to land to create a wave pattern? If it goes through hole 1, how does it know that hole 2 is open? If hole 2 were closed, the electron would just make a simple pile behind hole. But because hole 2 is open, the electron somehow knows to avoid certain spots on the screen, the dark spots in the interference pattern. It is as if the electron leaves the gun, looks at the two holes, goes through both of them at once, like a wave, interferes with itself, decides where it is allowed to land, based on that interference, and then suddenly remembers it is a particle, and lands at one single point. Does it go through hole 1? No. If it did, there would be no interference. Does it go through hole 2? No. Does it go through both? If we look at it, we only ever find it as a single lump. Does it go through neither? Impossible. It hits the screen. This is the central mystery. The electron behaves like a wave when it is moving, but it behaves like a particle when it arrives. It is a wave of probability that travels through space, passing through both slits, interfering with itself, and then collapsing into a single location when it hits the detector. Now you might be thinking, this is just a trick. The electrons must be talking to each other or bouncing off the edges. So let's try to outsmart nature. Let's spy on them. We put a bright light source right behind the slit. If an electron goes through hole 1, we will see a flash of light near hole 1 as it scatters the light. If it goes through hole 2, we will see a flash near hole 2. We are going to watch exactly which hole the electron goes through. We will catch it in the act. So we turn on the light. We fire the electron. We see a flash near hole 1. Aha! We say, it went through hole 1. We fire another flash near hole 2. Okay, that one went through hole 2. We do this for thousands of electrons. We successfully track every single one. We have a list. This one went through hole 1. That one went through hole 2. But then we look at the back screen. The interference pattern is gone. The moment we look to see which hole they go through, the electrons stop behaving like waves. They go back to behaving like bullets. We see two simple piles on the screen. The stripes disappear. Nature essentially says, oh, you are watching. Fine, I will act like a normal particle. When we don't look, the electron explores both paths. When we look, we force it to choose one path, and that destroys the interference. It seems that the act of measurement, the act of interacting with the electron to see where it is, changes the outcome of the experiment. You cannot observe the world without changing it. This is not because our instruments are clumsy. We could build the most delicate, gentle sensor in the universe. It wouldn't matter. The rule seems to be built into the fabric of reality. You can know which path the electron took, or you can see the interference pattern. You cannot have both. So how do we do physics in a world like this? How do we calculate anything if particles are acting like waves, and waves are acting like particles? We had to invent a new way of thinking. We had to throw out the old rules of probability. In the old world, the classical world, probabilities simply add up. If there is a 5% chance the bullet goes through hole 1 and hits a certain spot, and a 5% chance it goes through hole 2 and hits that same spot, the total probability is 5% plus 5%, which is 10%. Simple addition. In the quantum world, this failed. If we just added the probabilities, we would get the two piles of bullets. We wouldn't get the dark spots where the waves cancel out. To describe the electron, we use something called a probability amplitude. You can think of it like an arrow on a piece of paper. It has a length, and it points in a certain direction. This is where the math comes in, the complex numbers and the calculus you might hear about. But you don't need to do the calculus to get the idea. Just think of arrows. Every way the event can happen has its own arrow. There is an arrow for electron leaves gun, goes through hole 1, hits the screen. There is another arrow for electron leaves gun, goes through hole 2, hits the screen. In the classical world, we add the probabilities. In the quantum world, we add the arrow. If you have two arrows pointing in the same direction, and you add them, placing them tip to tail, you get a giant arrow. This is a bright spot on the screen. Lots of probability. But if you have one arrow pointing up, and the other arrow pointing down, and you add them, they cancel out. You get 0. No arrow. This is the dark spot on the screen. The electron has a 0 chance of landing there, even though it could have landed there if only hole 1 was open. This is the magic recipe. We calculate these arrows, these amplitudes, for every possible path the particle could take. We sum them all up, and then only at the very end we square the length of the final arrow to find the real probability of finding the electron there. This method, adding amplitudes instead of probabilities, is the great secret. It explains the interference. It explains why atoms are stable. It explains lasers and computer chips. It is the language nature speaks. It tells us that until we look, the electron is not a thing in one place. It is a bundle of possibilities, a collection of arrows pointing in different directions, all dancing and interfering with each other. It is strange. It is uncomfortable. It implies that the world is not solid and definite until an interaction happens. But it is the only way to explain what we see. And once you get used to thinking in arrows instead of rocks, it starts to have a beauty of its own. You start to see that the solidity of the chair you are sitting on is actually a miraculous balance of these interfering probabilities, billions of tiny arrows canceling and adding up to create the illusion of a solid object. We have stepped through the door of the mystery. We have seen that particles are waves, that observation changes reality, and that to predict the future, we must sum up every possible history. It is a wild world down there. But we are not done yet. We have only looked at a simple electron moving through space. What happens when we try to apply these rules to light, to electricity, to the forces that hold the universe together? That is where things get really fast and really precise. That is where we need to sharpen our pencils and draw some pictures. We have talked about arrow. We have talked about how an electron isn't just a rock, but a bundle of possibilities that explores every path it can. But I mentioned something earlier about sharpening our pencils. We need to talk about how we actually do this. Because when I say add up the arrows for every path, that sounds like a nice philosophical idea. But if you actually try to do it, you run into a problem. How many paths can an electron take to get from here to there? It could go in a straight line. That is one path. It could go in a slight curve.
That is another. It could go up to the ceiling, do a loop-the-loop, and come back down. It could go to the moon, circle it 3 times, and return. It could go to the edge of the universe and back. The number of paths is infinite, and not just a lot of paths. It is a smooth, continuous infinity of paths. If you try to draw an arrow for every single one of them, and add them up by hand, you will be sitting there until the universe ends, and you still won't have the answer. This is where the mathematics comes in. This is why you see those squiggly lines and symbols on the chalkboard behind me. You see that tall, stretched out S symbol. That is an integral sign. In the language of calculus, an integral is just a fancy way of adding up a lot of tiny little things. When we have an infinite number of paths, we can't do simple addition. We use calculus to smooth it all out. We use that math to sum up the arrows for every possible route the particle could take through space and time. And there is another equation you might see up there, one that looks a bit scary. It has a gamma symbol and a psi. That is the Dirac equation. Paul Dirac was a strange, brilliant man who wanted to describe the electron, but he didn't just want to describe it as a wave. He wanted to describe it in a way that obeyed the laws of relativity, the laws of fast-moving things that Einstein figured out. Dirac stared at the fire in Cambridge and came up with this equation. It was a guess really, but it was a guess that worked. It told us things we didn't expect. It told us that electrons must spin, like little tops, forever. It told us that for every electron, there must be a twin, an anti-electron, or positron. If they meet, poof, they turn into pure energy. It was all there in the math. The math is just a machine. You put the rules in one end, the rules about amplitudes and relativity, and you turn the crank. The Dirac equation is the crank. But even with Dirac's equation, we still had a problem. We knew about electrons, and we knew about light, but we didn't know how they talk to each other. We didn't know how light and matter interacted. Think about it. Almost everything you experience in the world is the interaction of light and matter. The reason you can see me right now is that light is bouncing off my suit and hitting your eye. The reason you don't fall through your chair is that the electrons in your pants are pushing against the electrons in the chair seat using electromagnetic force, which is really just exchanging light. Chemistry, biology, the burning of stars, it is all electrons and photons dancing together. We needed a theory for that. We call it quantum electrodynamics. QED, it is a terrible name, but we are stuck with it. QED is the theory of light and matter, and it is the jewel of physics. It is the most precise theory ever invented by human beings. To understand QED, you don't need the heavy integrals. You just need to understand 3 simple actions. Everything in the universe, all the complexity of life and stars, comes down to these 3 actions happening over and over again. Action number 1, a photon goes from place to place. A photon is a particle of light. Action number 2, an electron goes from place to place. Action number 3, an electron emits or absorbs a photon. That is it. That is the whole game. An electron moves along, and suddenly flash it, spits out a photon. Or a photon comes along, hits an electron, and gulp, it is absorbed. Now calculating this used to be a nightmare. You had pages and pages of algebra. It was easy to make a mistake. You would lose a minus sign somewhere, and the whole thing would explode. I am a lazy man. I don't like doing algebra if I don't have to. I like pictures, so I started drawing little diagrams to help me keep track of the math. We call them Feynman diagrams now, but to me, they were just sketches. Here is how you read one. Imagine time flowing from the bottom of the page to the top. You draw a straight solid line for an electron, so a line going up is an electron moving through time. You draw a squiggly wavy line for a photon, and the magic happens where they meet. You draw a vertex, a junction point. A straight line comes in, a squiggly line comes off it, and the straight line continues. That is an electron emitting a photon. Every line corresponds to a specific rule in the math. Every vertex corresponds to a specific number. That number is roughly 0. We call it the coupling constant. It is just a number that tells us how likely it is for an electron to spit out a photon. It's the probability amplitude for that specific event. So if I want to calculate the probability of 2 electrons bouncing off each other, I draw the picture. Electron 1 comes up, electron 2 comes up, electron 1 spits out a photon, squiggly line, the photon travels across, and hits electron 2. Electron 2 absorbs the photon, and gets knocked sideways. Electron 1 recoils, and goes the other way. This is a diagram of two electrons scattering. To find the probability, I just look at the picture. Two vertices. That means I multiply the coupling number twice. I include the arrows for the paths of the electrons and the photon. I sum it up. But wait, remember the rule from the double slit experiment. The electron takes every so if we want the true answer for how two electrons bounce off each other, we have to consider every possible way they could exchange energy. The simple picture I just described is the most likely way. One photon is exchanged. But what if they exchange two photons? I draw that diagram. What if they exchange a photon, and then that photon splits into an electron and a positron, which then annihilate each other and turn back into a photon before hitting the other electron? I draw that diagram too. What if electron 1 spits out a photon, and then catches it again, itself, before interacting with electron 2? Yes, even that. These more complicated diagrams represent much smaller probabilities, because every time you add a vertex, you are multiplying by that small number. So the more complicated the mess, the less it matters to the final answer. But if you want to be precise, if you want to be exactly right, you have to include them. This is where the advanced part of the science comes in. For a long time when we tried to calculate these complicated diagrams, the ones with loops and extra photons, the math gave us a ridiculous answer. It gave us infinity. You would add up the terms and get 1 pole 0. The mass of an electron is not infinity. The charge is not infinity. We knew the theory was right, but the math was broken. It took a lot of clever people, Julian Schwinger, Shinichiro Tamanaga, and myself, to figure out how to handle this. We developed a trick called renormalization. It sounds fancy, but it is basically a way of recognizing that the bare electron, the electron without its cloud of photons, is something we can never see. We only ever see the electron with its cloud. By carefully redefining what we meant by mass and charge, we could get the infinities to cancel out. We could subtract the nonsense infinity from the equation and leave behind a real finite number. Some people think this is a shell game. They think we are cheating, but the proof is in the pudding. Does it work? Let me give you an example of how well it works. There is a property of the electron called the magnetic moment. It basically measures how much the electron acts like a little magnet. We can measure this in the laboratory with unbelievable accuracy. We put electrons in a magnetic trap and watch them spin. We get a number with 12 decimal places. Then we go to our desks. We use QED. We draw the diagrams. We draw the simple ones. We draw the ones with 1 loop. We draw the ones with 2 loops, 3 loops, 4 loops. The calculations are massive. They take supercomputers years to compute the integrals for the most complex diagrams, and we get a number. When we compare the number from the experiment with the number from the theory, they agree. And they don't just agree a little bit, they agree to more than 10 decimal places. To give you an idea of what that means, if you measured the distance from New York to Los Angeles, and you measured it with this kind of accuracy, you would be right to within the width of a single human hair. That is how good QED is. It is the most successful theory in the history of science. It is not just a guess, it is the real deal. It tells us that these strange rules, these arrows, these interferences, these sums over histories, are actually how the universe are. So where does that leave us? We started with bullets and water waves, things you can touch and see. We found that when we look closely, matter dissolves into a strange dance of probabilities. We found that we cannot say the electron is here, or the electron moved there. We can only say here is the amplitude for it to be here, and here is the amplitude for it to be there. We found that the only way to predict the future is to sum up every possible version of the past. It is a world that feels shaky. It feels like there is no solid ground. You might ask, but Richard, why is it like that? Why does nature use amplitudes? What is the machinery behind the curtain? And I have to be honest with you, I don't know. Nobody knows. We have found the rules for calculating the answer, but we haven't found the reason for the rule. Maybe there is no reason. Maybe that is just the way it is. People often ask me if this makes me feel less amazed by the world. They ask if knowing the math takes the beauty away from the sunset or the flower. I say, it only I can see the flower as you see it, red, beautiful smelling of life. But I can also see the deeper beauty. I can see the redness as a specific frequency of photon generated by the electron transitions in the pigment molecule. I can see the structure of the petals held together by the quantum forces we just discussed. I can see the sunlight falling on it, a stream of particles that have traveled from the nuclear furnace of the sun, obeying these crazy laws of interference, to land right there on that leaf. It is a layered beauty. The world is a hierarchy of wonders. You have the beauty of the whole flower, the beauty of the cells, the beauty of the molecules, and down at the bottom, this strange rhythmic mathematical beauty of the quantum world. You don't need to understand the advanced calculus to appreciate this. You don't need to be able to solve the Dirac equation. You just need to hold this idea in your head. The world is not made of hard, dead stuff. It is made of vibrant, vibrating possibility. It is a game of chance, played by strict rules. If you find this confusing, good, you are paying attention. As I said at the start, I cannot explain why the world is this way. I can only tell you that it is this way. The more you look at it, the more mysterious it gets, and the more wonderful it gets. So the next time you look at a light bulb, or a magnet, or just your own hand, remember the arrows, remember the swarming, infinite path that the particles are taking every single nanosecond just to keep you existing in this shape. Remember that reality is a sum of all possibilities. We've come a long way from the doubles. We have walked through the valley of the strange and climbed the mountain of QED, and yet we are really just scratching the surface. There are still mysteries, gravity, dark matter, the beginning of the universe. But we have the language now. We have the tools. We know how to ask the question. Thank you for listening to me ramble about this. It is the most fun stuff in the world to think about. I hope you go away and think about it a little bit too. Nature is a fantastic thing. Don't be afraid of her weirdness. Embrace it. It's the only way to really see her.